David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember you can adjust the playback speed to make it faster or slower as you like. Second, you can pause the video at any point to catch up on your notes or jot down some questions. Third, you can turn on the captions so you can read my words on the screen. Today's lesson, antiderivatives. So we're working through our pre-calculus unit. You've had a derivative rule. We've played with derivatives for quite a bit up till now. And now we're going to just work on antiderivatives, which is actually just going backwards. These are inverse operations, just like multiplication and division are inverse operations, just like addition and subtraction are inverse operations. Derivation and antiderivation are inverse operations. We're going to get a better word for it than antiderivatives in a little bit. So let's review the derivative rule. This was, if you had a coefficient times x raised to a power, the derivative of this function is just going to be bring the exponent down and multiply it by the coefficient in front of x and reduce the exponent by 1. Okay? And what we did is we did a problem here where we took the derivative of x squared, and that just ended up being 2x. Now here's an interesting thing. The derivative of x squared plus 5 is also just 2x, because a constant goes to 0. Think about it this way. This is really action. The constant goes to 0 because this is really 5x to the 0 power, right? Because anything to the 0 is 1. So this is just 5x to the 0, which is just 5. You take your power down and multiply it by the coefficient, and that's going to turn the whole thing into 0. So a constant just goes away. So these two functions, x squared and x squared plus 5, have the same derivative. And this makes sense because in the function x squared, this is the quadratic function, all the 5 does is move the graph around on the coordinate plane. It doesn't change the shape of the graph. So the derivative function is still going to be the same because the slopes of the graph aren't changed by this constant that's hanging out here. Okay? Now, let's start going backwards. What if I gave you the function 2x and said, what's the antiderivative of that? In other words, what function's derivative is 2x? So if we go backwards, we know from here right away that the antiderivative of 2x is just x squared. But we also know from this discussion that another antiderivative possibility is x squared plus 5, etc. We could have any constant out there. So for that reason, this is called indefinite derivation or antiderivatives. So you don't know, you never know what the constant might be. So sometimes what we do is we might write x squared plus c, just to acknowledge that there's possibly a constant out there that we're never going to find when we do the antiderivative, because it's just not preserved when we took the derivative in the first place. Okay, let's look at the rule for taking antiderivatives, which is really just the process of integration. Okay, so we're not going to talk about antiderivatives anymore, we're just going to talk about integration. So that's antiderivatives and integration. Here's a new symbol for you. This is the integral sign. It's kind of like a stretched SE kind of thing. This is an integral sign. Now here's our rule. X to the n. There's our function. dx just stands for change in x. So this is just part of the notation. Here's our function, x to the n. The integral of that is going to be 1 over n plus 1 times x to the n plus 1. And this kind of makes sense because when we took the derivative, we were subtracting 1 from the exponent. Here we're adding. When we took the derivative, we are multiplying the old exponent by the coefficient. Here we're dividing by the new exponent here. Okay, so it kind of makes sense that way. So let's do an example. What's the integral of x squared dx? So this is just the function x squared. What's the integral? Let's do a quick plug-in with our formula. It's going to be 1 over, remember the power is n, so in this case it's 1 over n plus 1. Here's my power, so it's 1 over 2 plus 1 x, that's my x, to the n plus 1. Again, my n is 2, so it's 2 plus 1. So this is going to be x to the third over 3. So that's the integral of x squared. And the way you check it is if you want to, if you'd use the derivative rule on this, you should get right back to where you started from. So let's do that. The derivative rule says take the power, multiply it by the coefficient. So I got 3 times, reduce this by 1, and I still have my over 3. These cancel, and we're back to x squared. Okay, let's do a few more complicated problems. But first I want to call your attention to a couple things. First off, here's our integration formula. Okay, we did that on the last board. You're going to need to understand and be able to use fractional exponent rules. So x to the 1 over n, that's some fraction. That's going to be the nth root of x. So x to the 1/2 power is just the square root of x. X to the m over n, this is a fraction that's not got 1 on the top, some other number, that's going to be the nth root of x to the m. So we're going to use both of these rules frequently when we analyze these powers, because you can tell probably from our formula, we're going to get some fractions going on in here, and we're going to have to evaluate them. Okay, so let's take a look at this. X to the 1/3 power dx. What's the integral of that? So we're going to go ahead and use our formula. It's going to be 1 over 1 plus 1/3, that's our power, times x to the 1 plus 1/3. So if these problems are like not feeling really good at the start, just do a really good plug-in step like that. Don't do any math yet, just do your plug-in step, make sure it matches the rule, and then go forward. So let's do some simplification. This is going to be 1 over 1 plus 1/3 is 4/3. So now I have a compound fraction, and then I have x. This is also 4/3. Okay, so now what can I do? Well, 1 over 4/3 is going to be the same as 3/4. We flip the bottom fraction and multiply it. And then I have x. I'm going to get the 3rd root of x to the 4th. Okay? Now, I'm almost done. I think a better way to express this answer would be 3rd root of x to the 4 over 4, like that. So that would be the answer for that one. Okay, let's do another one. Here's x to the -4 dx. Now I want to call your attention to one more power rule that you're going to need to know. X to the minus n, negative power, is just 1 over x to that same power, but now positive. That's all that is, okay? So let's take a look. X to the -4 dx. We're going to go ahead and do our plug-in step. It's going to be 1 over -4 plus 1 times x to the -4 plus 1. Okay, I think this one's pretty straightforward. Now we're going to get 1 over -3 times x to the -3. Now, there's a convention we have with powers. We don't want negative powers. We want to convert that over to something that's only positive. So check this out. We're going to get 1 over -3x to the 3rd, just like that. Okay, let's do a more complicated problem. 3rd root of x all raised to the 4th power dx. So before we tackle this one, I want to show you yet another exponent law that's super helpful in dealing with these. If I have the nth root of x all raised to the power m, I can stick that power on the x under the root sign. So you could take the nth root of x and raise it to the power, or you could raise x to the power and then take the nth root, same thing. But this allows us to do something else, okay? So I'm going to rewrite this integral in a different way. This is going to be the 3rd root of x to the 4th dx. And I can rewrite this integral in another way. Using this rule here, I get, this is x to the 3/4 power, right? To the 4/3 power dx. So now I have something that's much more simple that I can then evaluate using my integral rule. Action. So let's continue on down. So now I'm going to plug in my integral rule, this one, I'm going to use that to do my plug-in step. So this is going to be 1 over 1 plus my power, 4/3, x, and then take my my power on my x, my 4/3, and add 1 to that. So 4/3 plus, actually we're supposed to go the other way. So 1 plus 4/3. Now this might look messy, but we're going to make it nice, okay? So this is going to be 1 over 4/3 plus 3/3 is 7/3 x to the 7/3. Okay, so I'm almost there. Let's do another step. 1 over 7/3, flip the bottom and multiply, is going to be 3/7. X to the 7/3 power is the third root of x to the 7. Okay, I'm just using this exponent rule there. Now let's just clean it up and make it look better. 3 times the third root of x to the 7 over 7. That's our answer. Okay, here's an interesting one. What's the integral of 5 dx? That looks kind of strange. There's no x here, but we can rewrite this integral so that there is one. Can you think of how to do that? If you thought about x to the 0, you're right. So this is going to be integral of 5x to the 0 dx. Okay, so now that I have it in this form, I can go ahead and apply my derivative rule. So this is going to be 1 over 0 plus 1, 5x to the 0 plus 1. Bring the 5 along. We're going to get 1 over 1 is just 1, so that stays, the 5 is right there, to the x to the 1. So the integral of 5 dx is just 5x. Okay, let's do one that's just a tad more complicated. Now we have two terms in our function. So this is 3x cubed plus 2x squared dx. We're going to take the integral of that. So all we're going to do here is we're just going to apply the integral rule to each of these terms separately. That's all you do. So it's just like doing two problems kind of in one. So let's do that. I'm just going to carry it on down here. This is going to be 3 over 3 plus 1 x to the 3 plus 1, using our rule there, plus 2 over 2 plus 1 x to the 2 plus 1. Now we can simplify. This is going to be 3 over 4 x to the 4 plus 2 over 3 x to the third. Simplify that down. We're going to get 3x to the 4 over 4 plus 2x squared over 3. And that's our integral of that function. Now that you've watched the video, take a moment to jot down any additional notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.